Yeah, let's continue our discussion on the modes in a parabolic index slab waveguide, right? That we sort of started in the last class. Right, so basically we said that the index follows the square law profile, right? So n square of x, or the directory constant follows the square law profile. Right, and we sort of wrote down the wave equation and looked for solutions, right? So, for example, we said that the TE modes the solutions will look something like this, right? So EY will be like Gaussian function times another function here u, right? And basically this u of psi we wrote down as a power series. Right, and then found these relations between the coefficients. Right, so this recursion relations between the coefficients. And so let's recall, so this psi was alpha times x, right? Alpha was A0 N1 that, and then this capital lambda here basically depends on the propagation constant that we are solving for. Right, so yeah, so basically we've taken sort of an infinite power series for u and then found these relations between the coefficients, right? So you can see that, I mean, if we let this run till infinity, then basically we have increasing powers of this position variable, right? So the function will sort of blow up, right? So we want the fields to decay to zero at far away from the center, right? So basically we want this series to terminate, right? So we don't want this to be an infinite series, but we want this to be a finite length series. Okay. So that would happen. You can see here, if at some particular r, this coefficient becomes zero, right? So r is integers, right? So we start from, let's say, a0, right? Then compute a2, a4, a6, so on, right? At some particular r, depending on this value of this lambda, if this becomes zero, right? So then the next coefficient will be zero, and then all further coefficients will be zero. Okay. So basically, if this capital lambda, you can see, if it's an integer, right? So if it's 2m plus 1 for some integer m, right? So m can take values 0, 1, 2. Right, so since r is also an integer, right, so when r becomes equal to m, then this coefficient will be 0. So that means a m plus 2 and all further coefficients will become 0. So only the coefficients up to a m will exist. Okay, so that will make this series finite. So it will have only n terms. Okay, so and another thing to note again here is, so this profile again, right? This is symmetric about x equal to 0, right? So n square of x is equal to n square of minus x. And we discussed previously that for such a symmetric profile, we can sort of classify the solutions into even and odd, right? So symmetric and anti-symmetric. We can do the same thing here, right? So if we start with r equal to 1 here, right? So then we'll get the odd terms, right? So a1, a3, a5, so on. So that will correspond to the odd solution, right? If we start with a0 here, then we'll get a0, a2, a4. That will correspond to the even. Okay. So basically, again, the mode index will be given by this value of n, right? So even ones will correspond to the even modes, and the odd will correspond to the odd. Okay, so this lambda again, so we can see here, right? It depends on beta. So for particular value of m, we get the propagation constant for that mode index n, right? So basically, beta for the TE mode, TE sub m mode, right? We can write like this. Right, so the mth mode propagation constant goes scales like that. So the beta square is proportional to m. Right, so if I plot, so if I look at, right, so beta square, the spectrum of beta square is equally spaced, right? So this is beta square for 0, beta square for 1, right? So it's equally spaced. So these are basically like, for example, the energy levels that you solve for a simple harmonic oscillator in quantum mechanics, right? You get energy levels which are equally spaced. Here, the corresponding quantity for the energy is beta square, as we saw from the eigenvalue equation last time. So you get a spectrum where beta square is equally spaced, okay? Where the spacing is given by this. Okay, and so one thing you can see from here is that, so recall, so when we were discussing ray paths, etc., we saw that how going to a graded index medium like this can help us reduce the intermodal dispersion, right? So the pulse broadening that we get compared to a step index, right? So the beta beta like that. Right? And if we again consider the index contrast to be small, basically this term is much smaller than 1, right? Because this is proportional to, you can see, square root of delta. So if delta is small, then this value is quite small compared to 1. So we can do a Taylor expansion of this and keep the first order term. Okay. So we just multiply this out and write k naught as omega by c. So we get this. Okay. Right. So under the weakly guiding approximation, or where the index contrast is small, we can see that the propagation constant, right, also now has values which are equally spaced. right? So yeah, and basically the dependence on frequency omega is just linear. Okay, and actually the frequency dependence does not depend on the mode index, right? Which means, so for example, if you take the, so you know the group velocity is basically the derivative of the frequency with respect to the propagation constant, right? So for the mth mode, the group velocity will be the derivative frequency with respect to the propagation constant. So if you look at what this 1 over the derivative of that, right? So if you look at d beta m by d omega here, right? So that is just a constant because it's a linear dependence, right? So this is just c over n1, right? So it does not depend on the mode index, which means what? That different modes are traveling at the same speed, right? It does not depend on modes. So all the modes are traveling at the same speed, which means under this approximation you actually have no broadening at all, right? Because all the modes travel at the same speed and reach the output at the same time. So that sort of shows you also from the mode picture that why gridded index or a square law medium like this has a lower dispersion than step index, for example. Right? Okay, so now, so let's look at these mode profiles that you get, right? So n equal to 0 will be the first mode, right? So m equal to 0 means just a0 is non-zero, right? So u of psi is just a constant, right? Right, which means the mode profile is just a Gaussian function. Right, so the lowest order mode, the mode profile looks like a Gaussian. Right, that's m equal to 0. Then the first order mode here, m equal to 1, which will be an even mode, right? So this means like lambda is 1, right? This capital lambda is basically 2m plus 1. This means capital lambda is 3. Right, so then here now this is a linear function. So right, so only a1, only the a1 term is non-zero, so that's a1 times psi. Right, so constant. Right, so now my mode profile looks like a linear function times a Gaussian. Okay, so now multiply this Gaussian by a linear function, so it becomes an odd function, right? So looks like that now. Right, and so on. So m equal to 2, you will get now something which has psi square. Right, so now a0 and a2 will be non-zero. So you get something like this. Right, and you see, so now this is a quadratic function, so it will have two zeros here, right? So at psi equal to plus minus 1 over square root of 2, this goes to 0. So it will have two zeros here, so it looks like that. So sort of the mode shapes are similar to what we get even for step index, right? Except that the functions are different. So the step index, you got sinusoidal functions in the middle, and then exponentially decaying here. but now we get these Gaussian functions multiplied by these polynomials, right? And these polynomials u0, u1, u2 are called Hermite polynomials. Okay, so basically um psi is basically just the Hermite polynomial of order m, that is denoted as h sub m. Okay, and so we can write a simple formula to generate the mth order Hermite polynomial. So it depends on the mth derivative of this Gaussian function. Okay, so the mth order Hermite polynomial you can generate by taking the nth order derivative of the Gaussian function and then multiply by Gaussian function. Okay, so this is the mth order Hermite polynomial. Right, so the solution, the mode profiles are Hermite functions times Gaussian function, which so they're known as Hermite Gaussian modes. So these are called AG modes. Right, and these functions are the same again as I've been saying that you get. So the wave functions that you get for simple harmonic oscillator are basically Hermite Gaussian, right, in quantum mechanics. Same. So, right, so basically, yeah, so for m even, the Hermite polynomials are even functions, and for m odd, you can see from here, right, that the Hermite polynomials are odd for m odd functions. So we can write sort of the modes in a normalized form. So basically like this. So some field amplitude, then a normalization constant times the Hermite polynomial times the Gaussian. Okay, and this normalization is done such that, so if we write this as some psi or psi, then basically the integral of where it is psi of x, then the integral of mod psi squared dx mod. So that this nm depends on the mode index m like that. Okay. So we saw here, I just erased that, but the effective index, which is basically beta over k naught, right? Is a decreasing function for m, right? Again, like when we saw for step index, and this is true in general for any wave, right? The lowest order mode has the highest propagation constant or the highest effective index close to the maximum value of the core, right? And then for higher order modes, the effective index keeps decreasing. So, right, if I plot the profile like that, right? So, of course, we assume sort of an infinite extent, so right, it keeps going, but for a natural structure, you'll terminate it at some value and then becomes constant, right? So then the first mode will have the highest, m equal to 0 will have the highest index. So this will be an effective square for mode 0, right? And the mode profile looks like a Gaussian function here. Right, so the next, so these will be equally spaced as we saw, right? So this one will look something like this. Right, and then depending on the index contrast, we have a certain number of modes, right? So again, so we are looking for n effective between the core and cladding, right? So the modes will exist up to some value of m. Beyond that, the mode index will become lower than whatever this value here is, right? Into square, and then that won't be guided anymore. So this one looks like that. Right, so so recall that we just solved for like an infinitely extended parabolic medium. We didn't actually solve for the parabolic index between minus a and a, and then a constant index beyond that, and then do boundary conditions. Right, that would be the more accurate way of doing it. But of course, that will become much more involved, right? But this approximate solution works very well for the modes which are far away from this cladding, right? So for this first 0 and first order modes, where n effective is close to this n1 square, this approximation of infinitely extended potential works very well, because basically it doesn't see much of this, right? It's basically sitting in the middle of the bottom of the well, sort of. And as you get closer to the cladding, so these modes will, the approximation will be weaker, right? So, and they'll also extend more into the cladding. Okay. So later on we'll see the modes in a square law medium optical fiber, right, with cylindrical geometry. So basically instead of x you have like an R here, right? And we'll see the modes will be similar. Okay. So that's why. And as we saw, the square law, at least to first order, leads to very low dispersion, right? So that's why they are important. So I think with this we'll end our discussion on planar slab waveguides. Any questions? Okay, so then now we move on to optical fibers. Right, so now we basically try to solve for modes in the cylindrical geometry of an optical fiber. So the exact solutions in a cylindrical geometry are quite complicated, as you can imagine, right? Because basically the wave equation, so the del square operator, etc., and cylindrical coordinates are of course much more complicated than the Cartesian coordinates, right? And there's one additional problem is that in Cartesian coordinates, like the unit vectors x, y, z are constant vectors, right? Which means at any point in space they point in the same direction, right? So the x cap vector is pointing in in the same direction wherever I draw the x cap vector. Whereas in the cylindrical case, like for example, if you take the r cap, the radial vector, that depends on where I am drawing the vector, right? So they are not all in the same direction. So which means that the unit vectors are actually not constant. So there's a question on n effective. Right? N effective is just the propagation constant divided by the free space wave vector. Right? So this free space wave vector is 2 pi by lambda, the free space wavelength, or lambda naught, right? Or omega by c. Right? So it's just telling you. So for example, like when a wave goes into a medium with refractive index n, you know that lambda becomes lambda over n, right? And k becomes basically k naught times n. Right, so for a homogeneous medium, that's true, like if the whole medium has the same index. But for waveguides, where you have a certain refractive index in some region and another refractive index in another region, right? And your wave sees partially this region and partially this region, right? So the mode profile extends both into the core and cladding, right? So you can imagine the wave to have some effective index here, n, right? So this beta is now k naught n effective, which depends on basically how much of the medium, how much of the cladding and the core relative to each other the mode is, right? So if the mode is very well confined, right, which means like, let's say it's not, most of the power is in the core, which happens for lower order modes, right, as we saw, then this n effective will be closer to n1. Right, to the core, because it's seeing most of the core. So n effective is almost, you can think of like a weighted average of the core and cladding refractive index, right? Because so n effective lies between n1 and n2 for guided modes, as we saw, right? And as the modes become weakly guided, so for higher order modes, now it's seeing more of the cladding, so then n effective goes lower towards n2, right? So that n effective is basically giving you sort of a metric of how well the mode is guided, right? How much of it is confined into the core. Please compare for graded and step index. Like, what do you want to compare? Sorry? Right. So we saw the modes. Yeah. So for, I mean, for so for the graded, so for the step index, basically, recall that we had to solve this transcendental equation, right, to get beta, right? So we had to solve these transcendental equations like this. Right, and the solutions of this basically gave us beta, right? So this C psi was like kappa v by 2 or something. This kappa was like square root of k naught square n naught square minus k, right? So in the step index case, actually, we didn't have an analytical formula that we could write down for beta, right? Because basically we had to solve this transcendental equation, and the solutions for that gave us beta. So if you wanted to plot for a particular step index, like the n effective spectrum, so you will get some numbers, right, depending on the solutions for this, right? Again, so recall, like we had these curves, and then basically there will be intersections here, right? And the intersections will give you these values. So first of all, they won't be equally spaced, right? So general properties hold true. Like for example, they lie between n1 and n2, right? And the lower order modes will be closer to n1, higher order modes will be closer to n2, right? But the spectrum itself will be different. So for step index, again, they won't be equally spaced, or yeah. So right. So for different refractive index profiles, you will get different spectrum of the energy. But the general properties hold true. So the well-guided modes, the lower order modes, have higher effective index, closer to n1. Higher order modes, which are less well guided have index closer to n, right? And the cutoff, as we saw, when this index becomes n2, is the mode cutoff. So beyond that, the mode is not guided. So that's true for any waveguide. So it's just that this particular value is an effective for the different modes. Where they occur depends on the particular refractive index profile. Right, and we saw that. So when the spectrum was equally spaced, that led to all the modes traveling at the same velocity. Right, the group velocity we saw was independent of mode number. In such a case where they are not equally distributed, right, the group velocities will come out to be different, and so it will have more dispersion in this case. No, NF, as I said, we just discussed, right? N effective is even for N effective is just so it's true for any waveguide. So we take any mode in any waveguide, find the beta, it will have a propagation constant, right? Because any mode you can, as we saw for any waveguide, so you have a cross section xy and mode is traveling in the z direction. So the mode profile you can write some function in the xy plane times a phase like that. Right? And this beta, what the values of this beta are, we solve from the wave equation. I mean, we had introduced this concept of N effective already for step index. So maybe, I don't know, you missed that class. And then we define this normalized index or normalized propagation constant also, right? Where sort of, so this we define like this, and B lies between 0 and 1, of course, for guided modes. So if B is closer to 1, it's again well guided, right? These modes. B is closer to 0 here, then it's the modes are not that well guided. Right, so and recall we got these BV curves, right? B versus B. So for different mode, for you take one particular mode, you get a curve like this. So this B, recall, is proportional to sort of the dimension divided by the wavelength. So either you change wavelength or you change the dimension. Right, so you take another mode, you get a different curve. Right? So for example, this n equal to 0, n equal to 1, n equal to 2, right? And the shape of these curves will depend on the refractive index profile, right? So for step index, I'll get some set of curves. If I go to a parabolic medium, these curves will look different. Okay. So the shape of these curves depend on the refractive index profile. Okay. Yeah. So now let's look at modes in a. So we'll start with the step index optical fiber.
Excuse me, sir.
Yeah.
So this factor delta, how small this can be?
It can go quite small. So typical optical fibers have 10 to the minus 3, right? So can go like in order of 10 to the minus 4. And upper range, of course, it can be like order of unity. Right? If you use two different materials, then the index difference is the order of the index itself. Right? So, but typically optical fibers have sort of in this range, like between 10 to the minus 4 and 10 to the minus 2 is sort of the maximum.
I asked because in the approximation that we made for the expression 1 minus x whole power 1 by 2, where we proved that
Yeah.
there we have a factor k naught by a. I'll have in the new denominator 1 by lambda naught a. Both are in microns. It will give rise to 10 power 12 or something, which is not that small compared to delta that I have. So it looking
So
not that.
K naught A, so K naught is 1 over lambda, right? So this is A over lambda. So that's basically telling you what is the size of your waveguide compared to the wave. Right? Again, so if this number becomes big, then you have a lot of modes. If this number is small, right? So if your size is only say 2-3 times the wavelength or something, or maybe 4-5 times the wavelength, right? And the index contrast is small, then you have only a couple of modes.
No, sir. For the expression that you have written for beta m previously, there you wrote k naught by a.
Mm, yeah, so that's so that's beta square, right? So beta square we wrote. So beta square of course has units of beta has units of per length, right? So beta square has units of per length square. So that's why you have k naught square here, right? And then you have k naught by a. Right? So what's the confusion? I don't get. So let's say if a is order of the of order of lambda, then k naught by a is sort of like k naught square. Right? If a is of the order of lambda, right? So a is like 1 over lambda. So here you'll get k naught square. Right? So if I take k naught square n1 square common out here, then I get something like 1 minus. So here I have square root of 2 delta divided by n1. Right? So here what we have is something proportional to delta, which is much smaller than 1. Is that clear?
Yes, sir. Previously you had written k naught by a by taking that common k naught n1 common. Also you wrote k naught by a. Now this expression is correct, sir.
Oh wait, yeah, maybe I wrote something. Right? I don't know.
And now it's fine, sir. Anyways, only thing is a should be there.
Yeah, so even when um, no, so there I had k naught a here, right? So when I take that approximation, so I had k naught a here. When I take the square root.
Yes, sir. Yes,
So
sir.
k naught is there.
Yeah. What I'm saying was previously you had written k naught by a, so it
Yeah, so
becomes
beta square has k naught by a, right?
no no. After that also you wrote it as k naught by a.
So okay, maybe I yeah. Okay, so this is the correct expression, right?
Yes, sir.
If I wrote it incorrectly, you can. I mean, so you take square root of this and take the Taylor expansion, so you get 1 minus half of 2 square root. I mean, yeah. So I mean, I could make mistakes while writing, so it's important that you go through your notes at home and check that. Don't take whatever I've written on the board as secret. Right? It's not. I could make mistakes while writing. So either you point it out in the class itself while I'm writing, or yeah, also go back and go through your notes carefully to see. That also helps you. Yeah, learn the material, right? So, okay. So now, the next topic is boards in the step index fiber. Right, so now we have cylindrical geometry. Right, a circular cross section. So radius A, and the core refractive index is N1, and then I have a surrounding region refractive index N2. Right, so again we can denote the propagation direction as Z. Right, and now the refractive index profile I can write in cylindrical coordinates, so it just depends on the radial coordinate. Right. There is no azimuthal dependence of the. Right, so because of the symmetry, use cylindrical coordinates. So R, phi, and Z. Right, so again, one thing to first note here is that, right, so when we write, for example, the wave equation, something like that, right? So now, so if we use Cartesian coordinates, right? So if we write E as some Ex, right? So then what happens is that we get three different equations, right? So this vector equation reduces to three different scalar equations, right? So basically, the component x cap will have del square Ex, right? So this is a scalar equation. Similarly for the y component, z component. And why is that? Because these x, y, z unit vectors are constant vectors, right? So del square, when I take Ex of x cap, I can just take x cap outside, right? Because x cap doesn't depend on position, right? Because it's always pointing in the same direction. Right, so I get scalar equations for the different components, right, which is what we've been solving. But now if I go to cylindrical coordinates, right, so if I write this as ER times R cap plus some E phi times phi cap, right, then the problem here is that these R and phi vectors are actually not constant vectors, right? So this is my origin, right? In this plane, so right, so I take this position here, the R like here. Now R vector points like that, right? So they are not the same, right? So similarly for phi, right? Depends on where you are. So the absolute direction in which it is pointing depends on position, right? So when I take, for example, this put this into the del operator, I can't just take. So when I do this, I can't just take R cap outside, okay? Because R cap itself depends on position, okay? So it will have a derivative. So you can see that we can't straight away now take different components and take the individual components. Then right, it can become really complicated because you'll have the scalar part which depends on the also the unit vector also depends. Only the z component you can sort of take z cap out because right z direction is independent of position. But the r and phi cap are sort of coupled to each other, right? So the derivative of r will give me something in phi, and the derivative of phi will give me something in r also. Okay, so if I want to just directly follow this kind of procedure, then it becomes really complicated because r and phi are not constant vectors. Okay, so I hope that's clear. Right, another way to see it is, so if I write the r and phi vectors in terms of the Cartesian vectors, right? So at a particular position, so right, I can write this position as x comma y or equivalently, right, r comma theta or r comma phi. Right, so the radial vector here, right, of course, I can write like this, right? So in terms of the constant vectors x and y, right? So now you can see it has position dependence. It depends on where I am, x. If I change the point x comma y, then this r, the absolute direction changes. Right? Similarly for phi. Okay. So yeah, we can just follow this procedure and then get different equations for ER if I get it. Okay. So the actual way, what we can to solve for the exact modes, what one does is that, so we recognize that Ez, the z cap is a constant vector, right? So which means we can get the scalar equation for Ez, right? So r and phi are covered, but Ez we can write a scalar equation like this. Okay, and then now we can solve for the modes. So we can take this in cylindrical coordinates and then solve again in the same way that we've been doing. So we did in Cartesian coordinates, but basically you get a scalar equation, you solve for Ez. Okay. Similarly, the same argument holds for H also, right? So you can solve for Hz. So you solve for Ez and Hz, you get the field profiles for Ez and Hz, and then using the Maxwell's equations, curl equations, etc., you find the other components from Ez and Hz. Okay, so you can actually show that once you have Ez and Hz, you can get all the other four components, Er, E phi, Hr, H phi, from just Ez and Hz. Okay, so that you can show just from the Maxwell's equations. So the way to solve for exact modes is to first solve for Ez, Hz, right? Again, same way like we did, solve the wave equation, get boundary conditions, etc. Right? And once you have expressions for Ez and Hz, then use the Maxwell curl equations to get Er, E phi, Hr. Okay, so that's the proper exact way to do it. Okay. But in most practical optical fibers, right, these index difference contrast N1 and N2 are very close to each other, right? So that delta, which is the normalized index contrast, as we discussed, is very small, right? Maximum usually it goes to is 10 to the minus 2, right? Usually it's 10 to the minus 3 range. So under this approximation, when the index contrast is very small, as we had discussed, for example, in slab waveguides, right, the modes can become almost transverse, right? So we saw this weakly guiding approximation. Right, so for delta, which I can write as N1 or N2, this is much less than 1. Then the modes are almost transverse. Right, we saw this explicitly for the slab waveguides, which means that they're almost TEM, right? The electric and magnetic field components are almost perpendicular, right? In other words, we saw that the longitudinal component, right, compared to the transverse component will be much smaller. Like similarly for magnetic field, let's say if you have EX and HY, right, the field components will be much smaller. Okay. So in the weakly guiding approximation, which is where most practical optical fibers are, we can assume the fields to be almost transverse, right? And just say, okay, primarily my field components are like EX and HY, and the propagation direction is Z, right? Or equivalently, like electric field is in Y and magnetic field is in Z. So these are the primary components. All the other components are negligible, right? We can assume to be zero first order. So under that approximation, when we already assume that these are the only field components, then of course we can write a scalar equation for them, right? Because we already said, okay, only EX exists, so we can write EX, this equation in terms of, right, or X. Right, so then of course the job becomes much easier, right? So now again we just directly solve a scalar wave equation in cylindrical coordinates now. So than the Cartesian coordinates for example the slab wave, right? But it's not that complicated like this, right? But again, thing to remember, this is approximate, which only works in this weakly guiding, right? Where the fields are almost transverse. For a general structure, for any N1 and N2, you have to follow that procedure that I said, right? Solve for Ez and Hz, and then use the curl equations and find the other field. Okay? So there the mathematics becomes a little bit more involved, but that's the exact variable. Maybe we'll discuss a little bit about that after we discuss this simpler way of solving in the weakly guiding approximation. So can TEM, right? Of course, we saw that purely TEM waves can only propagate in homogeneous media, right? As soon as you have some wave structuring of the refractive index, and so any sort of waveguide, right, where you have some now field profile, then we saw that you can't have purely TEM waves, right? You could have maybe TE waves or TEM waves, but not purely TEM, right? So that's the exact statement, right? If you have any waveguide, you cannot have TEM waves in them. But we also saw that under this approximation, where the index contrast is very small, the waves almost look like TEM because the longitudinal components are very small. Right? They were of the order of sort of, we saw this went as like the square root of delta or something. Right? So when delta is very small, right, 10 to the minus 3 or something, then we can say, okay, we can neglect the longitudinal components in comparison to the transverse components, and in that approximation, it's approximately TEM wave. It's not exactly a TEM. Right? So that's the statement. Right? Purely TEM waves can only travel in homogeneous media, but as soon as you have any structuring of the refractive index and any sort of waveguide, purely TEM waves cannot exist. But the longitudinal components become small if the index contrast is small, and they are all almost approximately TEM. Okay? So in optical fibers, since most fibers or almost all fibers operate in this regime, right? For various reasons that we've seen already, like dispersion, for example, is one important reason. We can use this approximation to solve for modes in this approximation, which work very well, okay? Because if this index contrast is very small, these approximate solutions work extremely well practically in like 99.9% of the cases, okay? So that's what we'll study first. But for some special cases, for example, you're using some special fibers with larger index contrast or some other kind of application or something, right? Then if you need the exact modes, then as I said, we have to start with Ez and NZ and solve for ER, the other components. So the longitudinal components Ez and Z are not identically zero, but in this approximation we can assume them to be small and say that it is. Okay. Right. So we can say in the weakly guiding approximation, we will have only transverse fields, right? So either Ex Hy or Ey Hx, right? So we assume the field. So for in this case, the field has a polarization in the x direction. Right. So this will be like x polarized mode, or you could have, in this case, the field is polarized in the y direction. Right, and because of this cylindrical circular symmetry, both these modes should be identical in terms of like the propagation constant, effective index. The properties should be identical because this is just a rotation, and the structure is invariant on rotation. Right, so these two modes, right, in terms of everything else, like their mode properties, just the polarization. And any superposition of these two modes will also give me some other polarization. Right? So we solve for these modes are known as LP or linearly polarized modes. Right? Because we are solving for modes where, so we are starting out solving for modes where the field is linearly polarized. Okay? But as I said, the exact solution, we'll discuss a little bit about that later. The exact solution won't have linear polarization. Okay? In fact, it won't have homogeneous polarization. The polarization will be dependent on position. Okay? But again, if the index contrast, like the contrast from N1 to N2 is small, then that variation is very small, and we can approximately say, okay, the polarization vector is sort of in the same direction mostly. Okay, another way to see it, for example, here is, so if you look at the boundary conditions, right? So for this kind of mode, so typically we use boundary conditions like at the boundary the field is tangential, the tangential field is continuous, right? Things like that. So you can see that here now, so at the boundary r equal to a, so we don't have the same boundary condition, right? So here in this region, so like phi equal to 0, so here the field is tangential to the boundary. Right. So, for example, here we can use the field is continuous condition. But now, if you look at here, so phi equal to 90 degree, the field is actually perpendicular. Right. So we can't use the field is continuous boundary condition here. We actually have to use. So, for example, perpendicular d perpendicular is continuous, right? And as you know, d is epsilon times e, so basically, and epsilon is n square. So n square times e. So at this boundary, n square times e will be continuous, right? Which is different from just e being continuous, because n is changing, right? So that's why you can immediately see here that like a linearly polarized mode like this cannot be the exact solution in a cylindrical symmetric geometry, right? Because you're getting different boundary conditions here, which cannot simultaneously be satisfied, right? But again, now if we go to this weakly guiding regime, so now n1 is almost equal to n2, so n square, right? So on one side you have n1 square, on the other side you have n2 square. So now if n1 and n2 are very close, this is approximately just saying that the field is continuous. Okay. So now I have sort of, okay, the field is continuous, boundary condition everywhere. Right. So under that condition, okay, then I can solve it. Okay, so that's the approximation we are working on. Okay, so next class so basically, yeah, we'll assume these kind of solutions, and solve for these LP modes, what their mode profile looks like, right? But thing to keep in mind, these are actually approximate solutions, but they work very well in the weakly guiding approach.